Newton's second law, unraveling the equation of motion. Newton's second law of motion, a fundamental principle in classical mechanics, provides a mathematical expression that quantifies the relationship between the force applied to an object, its mass, and the resulting acceleration. The equation encapsulating this relationship, F equals ma, lies at the heart of understanding the dynamics of objects in motion. In this video, we will explore the intricate details of Newton's second law equation, delving into its significance, interpretation, and broader implications for the physical world. 1. Newton's second law equation in context. The equation F equals ma represents a concise expression of Newton's second law of motion, which states that the acceleration of an object is directly proportional to the net force applied to it and inversely proportional to its mass. By quantifying the relationship between force, mass, and acceleration, this equation enables us to predict and understand the behavior of objects under the influence of external forces. 2. Components of Newton's second law equation. In the equation F equals ma, F symbolizes the net force acting on an object, m represents the mass of the object, and a signifies the resulting acceleration. The net force can be understood as the vector sum of all forces acting on the object, while mass characterizes its resistance to changes in motion. Acceleration, on the other hand, reflects how rapidly an object's velocity changes with time in response to applied forces. 3. Interpreting the equation. Essentially, Newton's second law equation suggests that the acceleration an object experiences is directly proportional to the force applied to it and inversely proportional to its mass. This implies that a stronger force will yield a greater acceleration, whereas a larger mass will result in a smaller acceleration. Furthermore, the equation indicates that acceleration and force possess the same direction, offering key insights into the dynamic behavior of objects. 4. Units of measurement. To maintain consistency, it is crucial to use appropriate units when employing the Newton's second law equation. Force is measured in newtons, n, mass in kilograms, kilogram, and acceleration in meters per second squared, ms squared. By adhering to these units, we can ensure accurate calculations, facilitating precise predictions and evaluations of motion. 5. Calculating force and acceleration. Newton's second law equation provides a systematic framework for calculating unknown quantities in dynamic systems. By rearranging the equation, we can determine force, F, when given the mass, m, and acceleration, a, or alternatively, solve for mass or acceleration when force and one of the other two variables are known. This equation empowers us to make quantitative predictions and interpretations of real-world phenomena. 6. Limitations and assumptions. While Newton's second law equation is a powerful tool for many scenarios, it relies on certain assumptions. When dealing with relativistic speeds or objects approaching the speed of light, classical mechanics breaks down, and alternative models, such as those provided by Einstein's theory of relativity, become necessary. Moreover, the equation assumes objects are point masses and neglects effects like drag or friction, limiting its applicability in certain contexts. 7. Connecting Newton's second law to real-world scenarios. The equation F equals ma enables us to explore a vast array of natural and engineered systems. From understanding the motion of planets in celestial mechanics to analyzing the acceleration of vehicles on the road, this equation plays a pivotal role across various scientific disciplines. Its application extends from investigating microscopic entities, such as atoms and subatomic particles, to analyzing macroscale phenomena, like the motion of projectiles or the behavior of fluid flow. 8. Supporting evidence and experimental verification. Newton's second law equation has been rigorously verified through countless experiments and observations. Scientists have conducted experiments involving objects of various masses, subjecting them to known forces and measuring the resulting accelerations. These investigations consistently support the relationship F equals ma, providing empirical evidence for Newton's insights into motion. 9. Widening perspectives, implications beyond classical mechanics. Although Newton's second law equation emerged within the framework of classical mechanics, its implications transcend this realm. In other areas of physics, this equation serves as a foundation for understanding the behavior of systems influenced by external forces. Its influence can even be seen in fields such as biomechanics, robotics, and more. For example, in biomechanics, Newton's second law is used to analyze the forces acting on the human body during movement, providing valuable insights for designing efficient and safe exercise programs. In conclusion, Newton's second law of motion is a profoundly influential principle in classical mechanics. It elucidates the intricate relationship between force, mass, and acceleration, enabling us to comprehend and predict the behavior of objects. As graduate students immersed in scientific inquiry, a deep understanding of this law is crucial to advance our knowledge and unravel the mysteries of the universe. Newton's second law paves the way for groundbreaking research and technological innovations, leaving an indelible mark on the realm of physics.